We're going to continue section 1.5A by this idea of those zeros and those x-intercepts, and we're going to use that to help create our graph or write an equation for our graph. So we're going to take a look at it, and we're going to take a look at our x-intercepts and kind of see where those are. And what we see is that it crosses here, and it crosses here. And we can see that this would be x equals 3, and it's odd, so it's probably only going to go once through the 3. But here we can see its tangent at x equals -2, so that means it's an even multiplicity. So this is a double root, so multiplicity there of 2. And so what does that mean? It means that our factors for our zeros are x equals -2, x equals -2, and x equals 3. So you notice that I list the x equals -2 twice because they do hold value when you're writing an equation. So when I go to do this, I'm going to say k of x equals, I'm going to leave a little space, I'll talk about that in a second, x plus 2, x plus 2, and then x minus 3. So again, they're the opposites because what should be happening is that when I solve it, I should be getting where that 0 is. Now, I left this blank because I don't know anything about the coefficient. Now, I can infer some things because we can see that it's going downward. So I'm guessing that it's going to be negative, but I don't know, is it -5, -200? I don't know what that coefficient is. So I'm going to leave that as A. So I have this here, and I don't exactly know what it is. But what we also know is that the y-intercept is about there. So we're going to make a note that the y-intercept is at 0, 2. So what does that mean? It means on this graph, we have an x value of 0 and a y value of 2. So let's try substituting that in. If I put in that for y, aka, let's change that actually to plug in the number right away, a 2. I don't know what the value of a is, but all of these x values are going to become 2 now, or I'm sorry, all those x values are going to become 0 now. Then take a look at what I got. I have 2 equals a times 2 times 2 times -3, or 2 equals -12a. And if I divide that out, now I have -1/6 equals a. Well, I just found that missing piece. So what I can do is I can go back to the beginning and plug that in, and now I have an equation for what k of x is. So k of x is equal to -1/6, because that's my a value. And then I'm going to clean this up a little bit, and I'm going to write this as x plus 2 squared. That implies that bouncing off, or that tangent at x. And then x minus 3. And hopefully that should make sense to us, because that leading coefficient is negative. So that, and the degree is 3, right? 2 right here, 1 right there. So our end behavior should be split. One going up, and then the other going down. The next little piece is we're going to talk about the conjugate root theorem. So when we have a function, and if that function is a polynomial with rational coefficients, meaning no imaginary numbers, no pi, square roots of 2, then the irrational roots of p of x equals 0 occur in conjugate pairs. That is when a plus square root of b is a root, then a minus square root of b is also a root. So they have to join in pairs. Here's an example for you. If I have, let's say, x minus square root of 2 times x minus square root of 2, I'm sorry, plus, you might have heard this, we're rationalizing the opposites, right, the conjugates. If you go to FOIL, I'm going to get x squared minus square root of 2x plus square root of 2x minus square root of 4. Well, what ends up happening is the middle numbers cancel out. And because you're squaring that, that's going to end up being a rational number. And you get like this nice, usually integer, it doesn't have to be, but rational number. So that's why you need this conjugate idea, is because I want those numbers to cancel out so it's nice and neat. The same thing happens when we have an imaginary number. If you have a plus bi, then a minus bi must also exist. Same idea, if you were to FOIL it, and then you end up getting, a plus bi, and then I go ahead and FOIL this, I get a squared plus abi minus, I'm going to run out of room. Let's see. I'm going to minus it down here, minus abi, and then becomes minus b square I squared. Well, these guys are going to cancel. That was supposed to be minus abi. Those guys are going to cancel because they're opposites. And then if you recall, I squared is just simply -1. So you end up getting rid of all those negative numbers. So again, if you see this guy, this has to exist. And the same thing happens with imaginary numbers. Now, the other little note here is that a polynomial function f of an odd degree must always have at least one real zero. So that should make sense, because if they're going in opposite directions, one of these lines has to cross through the x-axis. Whereas if they're both going up for an even degree, maybe they're sitting above the x-axis and they don't have to cross, or maybe they're pointing down, so they don't have to. But odd, they must at least cross once. So what number 6 is saying is that a polynomial function of degree of 5 whose coefficients are the real numbers has the zeros 2, 3i, and 1 plus I. It says find the remaining. Well, this is 1, this is 2, this is 3, so I'm missing 2. And what we talked about is that this always comes in a pair. So this pairing would be -3i. This pairing, the conjugate would be 1 minus I. And then this would be the fourth, and this would be the fifth zero of the degree. Okay, so we're trying to find the polynomial, kind of what we did in a couple examples ago, with a degree of 4, and they give us 3 of the zeros, so we need to find the fourth. So if I'm making a polynomial out of this, I'm going to do x minus 2 for the first one, x minus 2 for the second one, and then for here, I'm going to do x minus -3 plus I. And remember that missing one will be x minus -3 minus I. So that's the conjugate of that. So there's my fourth one. I'm going to clean this up by doing x minus 2 squared. And then I'm going to clean these up, and we're going to get x plus 3 minus I, and then x plus 3 plus I. Now, I probably wouldn't give you something this long to do in like on a test or a quiz, but we should be able to FOIL this one out. This one would be x squared minus 4x plus 4. This one, if you kind of think of it as a structure of a dot, so we have the x plus 3 squared, and then it's the I squared. That's going to end up giving you x squared plus 6x plus 10. And what would happen is you would need to distribute each one of these. So the x squared gets distributed here and here and here. And then you do the same thing with the negative 4x. Well, we're going to save some time. This ends up giving you x to the fourth plus 2x cubed minus 10x squared minus 16x plus 40. And it says graph the function. So you could go ahead and put that in. And then, or you could do the binomials. So go ahead, pause it, plug it in. I'm skipping around a little bit. This is kind of what that sketch looks like. You can, and it says analyze the characteristics. Well, a couple of things. Degree of 4, we see the end behavior, right? Both pointing up. We see a relative min at negative 2.78 at 23.95. So you can see that that's the relative min right there. This is the absolute minimum at negative 2.0 on your graph. And then negative 0.72 and then 45.86 is that relative maximum. We can see a y-intercept at 0.40 and x-intercept at 2.0. Now, one thing we talked about a little bit is the limit. So if we look at the limit, they're both going up. And the notation we should probably practice is, since they're both going up, the limit as x approaches negative infinity for function f, again, as it's going left, it is going up, so it's going positive infinity. But as the x values approach to the right, that's what this is saying, as this is approaching the right, the y values are going up. So that's kind of talking about what's happening with the end behavior. So this is just kind of going back a little bit to those roots of saying, all right, find the zeros of the function. How do you do that? You do that by solving. So what we're going to do is we're going to take this, set it equal to 0, and we kind of look and see what possibilities we have to solve. Well, it's 4 terms, so it's going to be grouping. I'm going to take out an x. I get x squared minus 3. I'm going to take out a 1, x minus 3. Sorry, I'm going to back up. I should take out an x squared right there. And then I regroup x squared plus 1 and then x minus 3. When I take the x squared plus 1 and solve for it, I get x squared equals negative 1. So x equals plus or minus square root of negative 1, which is plus or minus I. And then this would be x equals 3. So my zeros are 3, negative I, positive I, and then the factored form of this polynomial would be x minus 3, which is kind of what we did, but I'm going to break down the x squared plus 1 more. It's going to be x minus I and x plus I. For number 9, I'm going to ask you to pause the video and do the same sort of thing. I want you to factor this out and then find the zeros as well. A good hint to start this would be to factor out the GCF, and then you can take it from grouping. Okay, if you need to, pause the video double check that this is how you factor this down. You can see the zeros of them, where we got from over here. And then you can see that, and that should make sense. We have 3 zeros. The degree is 3 right there. All right, last question for this section. I know this was kind of a long one. Is number 10 is if x of 1 is a 0 of a function of f of x. For that one, write it as a product of a linear and reducible quadratic factors with real coefficients. I'm not 100% sure if you guys did this in Algebra 2 Trig last year. So if you didn't, please let me know so I can maybe go back over this a little bit. This right here is it's telling us that that is a factor, meaning that x minus 1 and then some other unknown 2 factors will give us 3x cubed minus x squared minus 7x. But we don't know what that is, and this is not factorable. So what we do is we can use long division or synthetic division. This is where I'm not sure if you remember synthetic division. So I put that number there, and I use synthetic division to help reduce it down. And what that does is it's going to bring this. So if you remember synthetic, this will be 3, this will be 2. Sorry, that should be -7. This will be -5, and this is -5, and then this is 0. And because this is the remainder, this brought down the quadratic, or this brought it down from a cube originally down to a quadratic. A quadratic which is actually factorable. So if you factor this is 3x plus 5 times the quantity x minus 1. So again, by doing synthetic division, what happens is it knocks it down a degree if you know at least one of those. And this can be really helpful with higher degrees. So what is our factored form of this completely? Well, we have the original x minus 1, and then I'm going to carry this over and have 3x plus 5, and then x minus 1. So then what are our solutions? Well, we have, or our zeros, we have 1, so it's a multiplicity of 2 there. What does that mean for the graph? It means it's going to bounce off the x-axis. And then I'm going to have -5/3.